Section 25.10 and 25.11. Section 25.10, bow waves. When the speed of the source in a medium is as great as the speed of the waves it produces, something interesting happens. The waves pile up. Consider the bug in the previous example when it swims as fast as the wave speed. Can you see that the bug will keep up with the wave crests it produces? Instead of the crests getting ahead of the bug, they pile up or superimpose on one another directly in front of the bug, as suggested in figure 25.19. The bug moves right along with the leading edge of the waves it is producing. Here's the bug, there's the leading edge. They pile up, which we call superimpose. The same thing happens when an aircraft travels at the speed of sound. In the early days of jet aircraft, it was believed that this pileup of sound waves in front of the airplane imposed a sound barrier, and that to go faster than the speed of sound, the plane would have to break the sound barrier. What actually happens is that the overlapping wave crests disrupt the flow of air over the wings, so that it is harder to control the plane when it is flying close to the speed of sound. But the barrier is not real. Just as a boat can easily travel faster than the speed of water waves, an airplane with sufficient power can easily travel faster than the speed of sound. Then we say that it is supersonic, faster than sound. A supersonic airplane flies into smooth, undisturbed air because no sound waves can propagate out in front of it. The sound waves aren't fast enough. Similarly, a bug swimming faster than the speed of water waves finds itself always entering into water with a smooth, unrippled surface. When the bug swims faster than the wave speed, ideally it produces a wave pattern as shown in figure 25.20. It outruns the wave crests it produces. The crests overlap at the edges, and the pattern made by these overlapping crests is a V shape, called a bow wave, which appears to be dragging behind the bug. The familiar bow wave generated by a speedboat knifing through the water is produced by the overlapping of many circular wave crests. Here's the figure. So here is the bug swimming faster than the water waves. The waves trail behind, and you can see along the edges they overlap and form this V-shape bow wave. Figure 25.21 shows some wave patterns made by sources moving at various speeds. Note that after the speed of the source exceeds the wave speed, increased speed produces a narrower V-shape. So here's the figure. That little weird symbol is a V. So this is saying V less than VW. VW is the speed of the water waves. So V is the speed of the bug. The bug is moving, but less than the speed of the water waves. And so these waves out in front stay ahead of the bug. When the bug speeds up, now the bug speed V is equal to the water speed, VW. So the bug keeps up with the leading edge of those water waves. They pile up and form that edge. If the bug speeds up even more, the bug speed V is greater than the VW. The bug speed is greater than the water wave speed. So the bug creates a wave and then pulls ahead of it, and makes another wave, pulls ahead of it, and pulls ahead of it. So the waves now are trailing behind the bug. So now they overlap, and we can see that we're seeing that V-shaped pattern trailing behind. That's the bow wave. If the bug speeds up even more, the V of the bug, the velocity of the bug, is much greater than the water waves. The waves spread out even more, they overlap even more, and the V shape stretches out farther behind. Notice when the bug's going faster, this V shape gets narrower compared to over here where it wasn't so narrow. That's it about bow waves. 25.11, shock waves. As we're about to see, shock waves are very similar to bow waves. A speedboat knifing through the water generates a two-dimensional bow wave. A supersonic aircraft similarly generates a three-dimensional shock wave. Just as a bow wave is produced by overlapping circles that form a V, a shock wave is produced by overlapping spheres that form a cone. So a shock wave is a cone shape. Just as the bow wave of a speedboat spreads until it reaches the shore of a lake, the conical shock wave generated by a supersonic craft spreads until it reaches the ground. The bow wave of a speedboat that passes by can splash and douse you with water if you're at the water's edge. In a sense, you can say that you are hit by a water boom. In the same way, when the conical shell of compressed air that sweeps behind a supersonic aircraft reaches listeners on the ground below, the sharp crack they hear is described as a sonic boom. Let's look down at the figure. Here's a plane going faster than sound. We know it's going faster because these sound waves behind it are overlapping, and they're forming the cone-shaped shock wave trailing behind it. If you're standing on the ground, when this shock wave sweeps over your ears, you hear the sonic boom just for a moment, and then it goes away. Back to the reading. We don't hear a sonic boom from slower than sound or subsonic aircraft because the sound wave crests reach our ears one at a time, and they are perceived as a continuous tone. They don't overlap. That's why they reach us one at a time. They don't pile up. They don't superimpose, and there's no shock wave. Only when the craft moves faster than sound do the crests overlap and encounter the listener in a single burst. The sudden increase in pressure has much the same effect as the sudden expansion of air produced by an explosion. Both processes direct a burst of high-pressure air to the listener. The ear cannot distinguish between the high pressure from an explosion and the high pressure from many overlapping wave crests. A common misconception, that means something that's wrong, a common misconception is that sonic booms are produced at the moment that an aircraft flies through the sound barrier, that is, just as the aircraft surpasses the speed of sound. This is equivalent to saying that a boat produces a bow wave only when it first overtakes its own waves. This is not so. The fact is that a shock wave and its resulting sonic boom are swept continuously behind an aircraft traveling faster than sound, just as a bow wave is swept continuously behind a speedboat. In figure 25.23, listener B is in the process of hearing the sonic boom. Here's listener B, and see how the V-shaped shock wave is sweeping over listener B. Listener A has already heard it a moment ago, and listener C hasn't heard it yet because it hasn't reached listener C's ears. The aircraft that generated the shock wave may have broken through the sound barrier hours ago, and it's just trailing that shock wave behind it. It is not necessary that the moving source emit sound for it to produce a shock wave. Once an object is moving faster than the speed of sound, it will make sound. A supersonic bullet passing overhead produces a crack, which is a small sonic boom. If the bullet were larger and disturbed more air in its path, the crack would be more boom-like. When a lion tamer cracks a circus whip, the cracking sound is actually a sonic boom produced by the tip of the whip when it travels faster than the speed of sound. Snap a towel and the end can exceed the speed of sound and produce a mini sonic boom. The bullet, the whip, and towel are not in themselves sound sources, but when traveling at supersonic speeds, they produce their own sound as waves of air are generated to the sides of the moving objects. By the way, the speed of sound is about 700 miles an hour. So when they talk about being supersonic, they mean things traveling faster than 700 miles per hour. On the matter of sound in general, you know that you'll damage your eyes if you stare at the sun. What many people don't know is that you'll similarly damage your ears if you overexpose them to loud sounds. Do as your author does when in a room with very loud music. Leave. If for any reason you don't want to leave, really enjoyable music or good camaraderie with friends, stay, but use earplugs of some kind. You're not being a wimp when you give the same care to your ears that you give to your eyes.